Intermolecular forces are forces of attraction or repulsion which act between neighboring particles. They are weak compared to the intramolecular forces, the forces which keep a molecule together. For example, the covalent bond, involving the sharing of electron pairs between atoms, is much stronger than the forces present between the neighboring molecules. They are an essential part of force fields frequently used in molecular mechanics. The investigation of intermolecular forces starts from macroscopic observations which point out the existence and action of forces at a molecular level. These observations include non-ideal gas thermodynamic behavior reflected by virial coefficients, vapor pressure, viscosity, superficial tension and absorption data. The first reference to the nature of microscopic forces is found in Alexis Clairaut's work Théorie de la figure de la Terre. Other scientists who have contributed to the investigation of microscopic forces include Laplace, Gauss, Maxwell and Boltzmann. Attractive intermolecular forces are considered by the following types: ion-induced dipole forces, ion-dipole forces, van der Waals forces. Information on intermolecular forces obtained by macroscopic measurements of properties like viscosity. Private data. The link to microscopic aspects is given by virial coefficients and Leonard-Jones potentials. Dipole-dipole interactions. Dipole-dipole interactions are electrostatic interactions between permanent dipoles in molecules. These interactions tend to align the molecules to increase attraction. An example of a dipole-dipole interaction can be seen in hydrogen chloride. The positive end of a polar molecule will attract the negative end of the other molecule and influence its position. Polar molecules have a net attraction between them. Examples of polar molecules include hydrogen chloride and chloroform. Often molecules contain dipolar groups, but have no overall dipole moment. This occurs if there is symmetry within the molecule that causes the dipoles to cancel each other out. This occurs in molecules such as tetrachloromethane and carbon dioxide. Note that the dipole-dipole interaction between two individual atoms is usually zero, since atoms rarely carry a permanent dipole. Ion-dipole and ion-induced dipole forces. Ion-dipole and ion-induced dipole forces are similar to dipole-dipole and induced dipole interactions but involve ions instead of only polar and non-polar molecules. Ion-dipole and ion-induced dipole forces are stronger than dipole-dipole interactions because the charge of any ion is much greater than the charge of a dipole moment. Ion-dipole bonding is stronger than hydrogen bonding. An ion-dipole force consists of an ion and a polar molecule interacting. They are aligned so that the positive and negative groups are next to one another, allowing for maximum attraction. An ion-induced dipole force consists of an ion and a non-polar molecule interacting. Like a dipole-induced dipole force, the charge of the ion causes distortion of the electron cloud on the non-polar molecule. Hydrogen bonding. A hydrogen bond is the attraction between the lone pair of an electronegative atom and a hydrogen atom that is bonded to either nitrogen, oxygen, or fluorine. The hydrogen bond is often described as a strong electrostatic dipole-dipole interaction. However, it also has some features of covalent bonding. It is directional, stronger than a van der Waals interaction, produces interatomic distances shorter than the sum of van der Waals radii, and usually involves a limited number of interaction partners, which can be interpreted as a kind of valence. Intermolecular hydrogen bonding is responsible for the high boiling point of water compared to the other group 16 hydrides, which have no hydrogen bonds. Intramolecular hydrogen-oxygen bonding is partly responsible for the secondary, tertiary, and quaternary structures of proteins and nucleic acids. It also plays an important role in the structure of polymers, both synthetic and natural. Van der Waals forces. The van der Waals forces arise from interaction between uncharged atoms or molecules, leading not only to such phenomena as the cohesion of condensed phases and physical adsorption of gases, but also to a universal force of attraction between macroscopic bodies. Keesom interaction. The first contribution to van der Waals forces is due to electrostatic interactions between charges, dipoles, quadrupoles, and permanent multipoles. It is referred to as Keesom interactions. These forces originate from the attraction between permanent dipoles and are temperature-dependent. They consist of attractive interactions between dipoles that are ensemble averaged over different rotational orientations of the dipoles. It is assumed that the molecules are constantly rotating and never get locked into place. This is a good assumption, but at some point molecules do get locked into place. The energy of a Keesom interaction depends on the inverse sixth power of the distance, unlike the interaction energy of two spatially fixed dipoles, which depends on the inverse third power of the distance. The Keesom interaction can only occur among molecules that possess permanent dipole moments, aka two-polar molecules. Also, Keesom interactions are very weak van der Waals interactions and do not occur in aqueous solutions that contain electrolytes. The angle averaged interaction is given by the following equation, where m equals charge per length, equals permittivity of free space, equals dielectric constant of surrounding material, T equals temperature, equals Boltzmann constant, and R equals distance between molecules. Dipole force. The second contribution is the induction or Dipole force, arising from interactions between rotating permanent dipoles and from the polarizability of atoms and molecules. These induced dipoles occur when one molecule with a permanent dipole repels another molecule's electrons. A molecule with permanent dipole can induce a dipole in a similar neighboring molecule and cause mutual attraction. Dipole forces cannot occur between atoms. The forces between induced and permanent dipoles are not as temperature-dependent as Keesom interactions because the induced dipole is free to shift and rotate around the nonpolar molecule. The Dipole induction effects and Keesom orientation effects are referred to as polar interactions. The induced dipole forces appear from the induction, which is the attractive interaction between a permanent multipole on one molecule with an induced multipole on another. This interaction is called the Dipole force, named after Peter J.W. Dipole. One example of an induction interaction between permanent dipole and induced dipole is the interaction between hydrogen chloride and R. In this system, R experiences a dipole as its electrons are attracted or repelled by hydrogen chloride. The angle averaged interaction is given by the following equation, where equals polarizability. This kind of interaction can be expected between any polar molecule and non-polar, symmetrical molecule. The induction interaction force is far weaker than dipole-dipole interaction, but stronger than the London dispersion force. London dispersion force. The third and dominant contribution is the dispersion or London force, which arises due to the non-zero instantaneous dipole moments of all atoms and molecules. Such polarization can be induced either by a polar molecule or by the repulsion of negatively charged electron clouds in non-polar molecules. Thus, London interactions are caused by random fluctuations of electron density in an electron cloud. An atom with a large number of electrons will have a greater associated London force than an atom with fewer electrons. The dispersion force is the most important component because all materials are polarizable, whereas Keesom and Dipole forces require permanent dipoles. The London interaction is universal and is present in atom-atom interactions as well. For various reasons, London interactions have been considered relevant for interactions between macroscopic bodies in condensed systems. Hamaker developed the theory of van der Waals between macroscopic bodies in 1937 and showed that the additivity of these interactions renders them considerably more long-range. Relative strength of forces. Note This comparison is only approximate. The actual relative strengths will vary depending on the molecules involved. Ionic and covalent bonding will always be stronger than intermolecular forces in any given substance. Effect on the behavior of gases. Intermolecular forces are repulsive at short distances and attractive at long distances. In a gas, the repulsive force chiefly has the effect of keeping two molecules from occupying the same volume. This gives a real gas a tendency to occupy a larger volume than an ideal gas at the same temperature and pressure. The attractive force draws molecules closer together and gives a real gas a tendency to occupy a smaller volume than an ideal gas. Which interaction is more important depends on temperature and pressure. In a gas, the distances between molecules are generally large, so intermolecular forces have only a small effect. The attractive force is not overcome by the repulsive force, but by the thermal energy of the molecules. Temperature is the measure of thermal energy, so increasing temperature reduces the influence of the attractive force. In contrast, the influence of the repulsive force is essentially unaffected by temperature. When a gas is compressed to increase its density, the influence of the attractive force increases. If the gas is made sufficiently dense, the attractions can become large enough to overcome the tendency of thermal motion to cause the molecules to spread out. Then the gas can condense to form a solid or liquid. Lower temperature favors the formation of a condensed phase. In a condensed phase, there is very nearly a balance between the attractive and repulsive forces. Quantum mechanical theories. Intermolecular forces observed between atoms and molecules can be described phenomenologically as occurring between permanent and instantaneous dipoles, as outlined above. Alternatively, one may seek a fundamental, unifying theory that is able to explain the various types of interactions such as hydrogen bonding, van der Waals forces and dipole-dipole interactions. Typically, this is done by applying the ideas of quantum mechanics to molecules, and Rayleigh-Schrödinger perturbation theory has been especially effective in this regard. When applied to existing quantum chemistry methods, such a quantum mechanical explanation of intermolecular interactions, this provides an array of approximate methods that can be used to analyze intermolecular interactions.